Hi everyone, so this video is the first video on the sets and Venn diagrams topic. So this video will be on sets and interval notation, and then the next few videos will cover more set notation and go into Venn diagrams. Sets. A set is a collection of numbers or objects. Each number or object is called an element or a number of the set. A capital letter is used to represent a set. So I've got an example there. If V is a set of all vowels, then V equals, and then we actually use the curly brackets to denote that it's a set. And then we just put A, E, I, O, U because they're obviously our vowels. A finite set is a set with only a certain amount of elements, like the one above with the vowels. It's only got those 5 elements in it. And an infinite set is a set which doesn't end. For example, the set of even numbers, because obviously even numbers go on forever. We have lots of symbols that go with sets and Venn diagrams. I'm not going to explain them all right now, but over the course of a few videos, you'll start seeing all these in different things, and then you'll start understanding when to use them. We have special number sets, and the first one is natural or counting numbers. And we use the big capital letters with like the double lines on them for this type of thing. So natural counting numbers uses an N, and they are all whole numbers from 0 upwards. No negative, positive numbers including 0. Within integers, we have just an integer, which we use Z. Then you have Z plus, which is positive integers, and Z minus, which is negative integers. And you can see there how we can write the sets. With the positive and negative, note 0 isn't a part of either of those because 0 is neither positive or negative. So 0 actually only comes into the general integer set. Rational numbers, we use the letter Q, and it's a set of numbers which can be written in the form P over Q, where P and Q are integers and Q cannot equal 0. Basically, a rational number is a number that can be written as a fraction. If you can write it as a fraction, it's rational. And obviously Q can't be 0 because you can't divide by 0. R is real numbers, and so you see the big R there, and that's any number that can be placed on a number line. So if we can place it on a number line, it's a real number. And at this moment in time, they're the only numbers we will look at. We don't look at complex numbers unless you pick a higher level maths. Nice little flow diagram there. We always love a flow chart. So if we've got real numbers at the top, from real numbers we can split into rational and irrational. So obviously, rational numbers are numbers that can be written as a fraction. Irrational numbers are numbers that cannot be written as a fraction. Irrational numbers are basically decimal numbers that go on forever. It's a decimal number that goes on forever and it's not reoccurring. It's irrational. Rational numbers is everything else. Then with irrational numbers, we can split it into integers and then our natural numbers. Now, as I quickly just said before, a recurring decimal is rational. Any recurring decimal we can write as a fraction, and I'm going to show you how to do that to show that it's rational. So here we've got 0.36 recurring. To show that this is rational, we're going to do the following. So first of all, we're going to define that we're going to let x equal 0.363636. Obviously that carries on going, 36. Now as there are 2 decimals reoccurring, I'm going to times that by 100. So we'll have 100x equals 36.363636, and that will carry on going. If there was only 1 digit reoccurring, you'd multiply it by 10. If there's 3 digits, you multiply it by 1,000. So it just depends on how many recurring digits with what you multiplied that x by. Now once we've done that, we're actually then going to minus x. So we've got the 100x, and we're going to minus x from that. Now our x from above was 0.363636. Now you'll notice here that if we minus those, the decimal places will actually all cancel out, and we end up with 99x, 100x minus x, equals 36. We rearrange that, x equals 36 over 99. 0.36 recurring as a fraction is 36 over 99, and we can simplify that to 4 over 11. If you really want to check that, put it in your calculator and see what you get. Interval notation. So often with maths, we don't like to use too many words, and we like to shorten things. To avoid having to list all members of a set, we can use a mathematical sentence. Now the notation starts with, we have our curly brackets, have an X, and that straight line. If you look back at the symbols from before, that straight line means such that. So what this actually means here is the set of X such that, because the curly brackets represent the set, we've got X and a straight line. This little example here, we've got X, the straight line, -3, less than X, less than or equal to 2, XER. Now what this means is the set of all real X values, that's the XER at the end, that's the set of all real values, such that X lies between -3 and 2, including 2. So rather than writing everything, that whole thing out in words, we can write it in a mathematical sentence, and as mathematicians it's just a bit quicker. Now when we're representing on a number line, generally we'll just be doing this with real numbers and integers or natural numbers, and there's two ways we will do this. This first one, when it's a real number, we draw the line above the number line. Now it is, X is greater than -3. Now it's not greater than or equal to, so when it's just greater than, we use a circle. And then X is less than or equal to 2, so when it's less than or equal than, we use a coloured in circle just so we can tell the difference between them. And then because it's real numbers, we draw a line to join them up. Then I just like to draw a line down to the numbers on the bottom. Now that represents every number between -3 and 2. Then our dots show us that it's not including -3, but it is including 2. Now the next one, I've got an integer one. So if you read this number 2 sentence, the set of all integers, because we've got X is an element of Z, and X such that X lies between -5 and 5. Now we notice here that it is just less than and greater than is no equal to, so we don't want to include -5 and 5. Now when it's integers, we have to do it slightly differently. We don't draw a line above. Because it's integers, we couldn't have 1.2. We can only have -4, -3, -2, -1, 0. We can't have all the numbers in between, so we can't draw a line above the number line as we did in the previous one, because that includes every possible number between those 2 points. With integers, we actually draw dots on the number line. So it will be coloured in dots all the way between -5 and 5. Now I haven't put dots on -5 and 5 because we're not going to include those. If you wanted to do an open dot, you could do, but it doesn't really matter. So you can have it like that, or if you wanted to, you could put open dots on either end to show it stops there and it can't be those values. It's up to you. But I prefer just to put the coloured in dots. Go to 2 examples of this. Write using interval notation. So now we've actually been given the diagram and we want to write the mathematical sentence. So for this first one, A, it's very similar to that example too. So we always start with our curly brackets. It's going to be X such that, now it's going between, if we look here, we've got 0, 5, this has to be 1, 2, 3, 4. Dots on the line, which mean they're integers. Now there are many different ways you could write this one. I'm going to put possibly 2 or 3, maybe 4 different ways you could write this and they would all be correct. The first one for me that comes to mind is that it would be 1 less than or equal X less than or equal to 5. Now it's integers. With integers, then we have to do X is an element of Z. That's one way. Another way you could write it would be, I'm still going to say I'm going to start at 1, it's going to be less than or equal to, because it can be 1. But this time I'm going to say it's less than 6, which would also make sense. Because less than 6 with the integers, the next number would be 5 that we could have. Another way would be actually to say that we're going to start at 0. So X would be greater than 0, and it could be less than 6. And then our final option would be that X is such that 0 less than, well, X is greater than 0, but less than or equal to 5. So 4 different options, they're all correct. You just do which one feels most natural to you. B, this is going to be like that first little example we did above. And we can look at that and we can see it's real numbers because the line's drawn above. Start with our set, our x, such that. Now we've got the coloured in circle on -3, which means that's going to be a greater than or equal to. There is an open circle on 6, which means that's just less than. Now with real numbers, you can write the x is an element of R, or you don't have to write it. If you see a set notation without what x is an element of in terms of its number system, then we assume it's real numbers. So both of these will be classed as correct. Something like integers, you have to write x as an element of z. And that is sets and interval notation.